Once we've gotten through all the conceptual understandings of hypothesis testing, the actual work itself is not at all complex or difficult. Find the appropriate sample statistic, compare it to the null hypothesis value, determine the relevant z or t or even chi-square score based on the comparison, either calculate the p-value and compare it to alpha, or know what the threshold value is for the appropriate alpha and compare said z or t or chi-square to that, and then make a measured claim regarding rejection of the null hypothesis or failure to reject the null hypothesis based on these results. The p-value step is a formal necessity, but in most cases we can look at the resultant z or t or chi-square value and know pretty much on the spot whether we're going to be within or further out from alpha. Let's run through one example of each situation to show how this is done and how simple it actually is to do. Suppose a soft drink company comes out with a reformulated seltzer recipe that they claim is preferred at a rate of 2 to 1 by regular seltzer drinkers. Our consumer testing organization is skeptical, assumes the rate is lower, and decides to test this claim. We set up a simple random sample of 200 people nationwide to compare the two drinks. Of this sample, 112 say they prefer the new formula. That's 56%, which is still a fair majority but not 2/3. Is this low number far enough away from 66.7% though for us to formally cast doubt on the manufacturer's claim? The null hypothesis is that 2 out of 3, or 66.7%, or a 0.667 proportion, will prefer the new formula to the old one. The alternative hypothesis is that the proportion is less than 0.667. N is 200. Our point estimate p-hat is 0.56. We calculate our standard error using p. The square root of 0.667 times 1 minus 0.667 divided by 200, which turns out to be 0.033325. Our organization's house alpha value for these tests is a pretty normal 0.05, and here it's one-tailed. 0.56 minus 0.667 is negative 0.107. Negative 0.107 divided by 0.033325 is negative 3.21. Our sample result is 3.21 standard deviations away from the null hypothesis value, which we know immediately is too far. 3.21 standard deviations below the null hypothesis value gives us a p-value of 0.0007. There is a 7 out of 10,000 probability of getting this result in a random sample if the null hypothesis is correct, which, just to be thorough, is substantially less than the house rule 5%. We reject the null hypothesis value and call foul on the manufacturer's claim. Let's try another one with quantitative data, and this one we'll set up as a clinical trial. One of the abiding maxims of popular dietary science is that consuming lots of garlic will keep your cholesterol level low. Anecdotal evidence suggests, or is said to suggest, that people who eat lots of garlic have consistently low-density lipoprotein or bad cholesterol scores. Let's test this folk wisdom and see how well it holds up. A simple random sample of 50 subjects was chosen to participate in the trial. 20 received a placebo, 30 took 300 milligram garlic tablets per day. The group's mean LDL value at the start of the trial was 166 milligrams per deciliter, the standard unit for cholesterol measurement. After 3 months, that mean cholesterol level in the treatment group had fallen to 163. The standard deviation of the group results was 12. Our null hypothesis is that mu after the treatment is 166 or unchanged. In an experiment, the null hypothesis is always that the treatment has no effect. Our alternative hypothesis is that mu is less than 166 since we expect it to go down. N is 30, point estimate x bar is 163, S is 12. We'll use a standard clinical alpha of 0.05. So it did drop, but did it drop by a meaningful amount? 163 minus 166 is negative 3. Our standard error is 12 divided by the square root of 30, or 2.19. Negative 3 divided by 2.19 is about negative 1.37, and we can disregard the negative from here. The threshold value for an alpha of 0.05 and 29 degrees of freedom is 1.699. We need to have a result further out from this. 1.37 is less than 1.699, and so we fail to reject the null hypothesis. Side note, even if we had been able to engineer this study to technically show statistical significance, say with a much larger sample size, the displayed improvement is not profound. Garlic keeps its place as a favored culinary aromatic, but not as a cholesterol treatment. The idea of developing an alternative hypothesis to a given standard deviation may seem kind of pedantic, but we actually can use this mechanism to determine whether a particular sample has a significantly different variance than a set population, which can be very important in trying to standardize and improve certain processes. The formula for a chi-square hypothesis test is an algebraic rearranging of the one from the confidence interval. Here, chi-squared equals degrees of freedom times the sample standard deviation squared divided by the population standard deviation squared. Find the appropriate alpha chi-square value or values, compare to the calculated result, and decide whether or not to reject the null hypothesis. Say we have a ceramics factory and a production process that makes plates that is notoriously inconsistent, which makes it hard to make predictions for supplies and shipping and other concerns. Batches of plates that are supposed to weigh 600 grams consistently show a standard deviation of 30 grams. If we refine certain parts of the process, we get the standard deviation of a test sample of 20 plates down to 12 grams. This looks impressive, but is this a statistically meaningful improvement, especially given a small sample size? Let's set everything up. Our null hypothesis is our population standard deviation, 30. Our alternative hypothesis is that we now have a standard deviation less than 30, so it's also one-tailed. Sample size is 20, point estimate is 12, alpha is, again, the now familiar 0.05. Chi-square equals 19 times 12 squared divided by 20 squared. Our chi-squared statistic is 6.84. Check the chi-square table at 19 degrees of freedom. Our alpha of 0.05 is read at the 0.95 column. The indicated chi-square value is 10.117. As our chi-squared value is substantially lower than this, we fail to reject the null hypothesis. Whatever we did to the process may have decreased the standard deviation, but not by enough, or more likely, not by enough in a large enough sample.